All right, for class 24, I have another example here. And this one's already been written out, so it'll go pretty quick where I just narrate. So a 2-pound sphere moving horizontally, it's a very heavy dodgeball maybe, to the right with an initial velocity of 12 feet per second strikes the lower end of a 4-pound rigid rod. The rod is initially at rest. The coefficient of restitution between the sphere and the rod is 0.8. Find the post-impact velocity of the ball. We get the mass moment of inertia of this big 3-foot rod. And so I think of almost like a really heavy yardstick. Since the x direction and normal direction are the same, we could drop the whole using the subscript normal. But we often, if it was a more complicated thing, we would want to break things down into tangential and normal. But we don't here because everything is pretty much in a horizontal direction. Okay, so got the mass moment of inertia, fine. Got the system momenta before, right? So apparently I found the figure where this thing came from. And we have the system external impulse that's happening. Notice that we should probably put the weight in here, but a lot of times we'll just ignore it because it is passing through right here. And we're about to take the momentum, right, about the angular momentum. So, and we're going to do it about A, so it's going to pass through there. And then we take a look, and a lot of times we will assume positive, but we've got to be careful that whatever we do, that we match up the direction of the angular one and what it would cause. The direction of the velocities of the rod have to agree right there. But a lot of times we will just assume the ball keeps moving in the direction that it started, and then we could find out whether it would bounce backwards if it's a negative number. So the conservation of momentum about the pivot A, we will find here. And so I've written here where we have this mass times the velocity, and they have the distance. I decided to call that LAB. And that's going counterclockwise, right? It's going wee that way. So we can take it as positive. And then nothing happens here, or everything will cancel out, and because it'll all be internal. And then we have the mass moment. We have linear momentum times that distance to the pin, LAB. And then, but we also have the mass of the rod times the velocity of the center mass of the rod, and it's the distance from it to the pin is LAB over 2. But we also have the rotational I omega prime. And we're able to, let's see, I guess in this particular instance here, we kind of left them to themselves. We'll fix them here in a second. But we put all the values in for this and got this equation. And then in order to get the coefficient of restitution, we must look at the velocity at the point of impact at B. Right, so that's the important thing right here. We can't use the coefficient of restitution at the place that we used up here, right? Those are going to be a velocity at the, let's say, at the center right here. We decided to go R is what they decided to use. And we use some kinematics to like fix those velocities, right? So the velocity to B that we're just mentioning right here that we're going to have to use for the coefficient of restitution is going to be omega times the entire length. We also know that, and so right here, that's the equation that we're going to stick back in there. We also need to replace this VR with omega times LAB over 2, right? So we can replace it here. So right there, I have reduced this equation right here to this one, and maybe we'll call that equation 1 because we're going to use that in a second. So there's 2 unknowns in equation 1 right there. And so maybe it was better. I'll call this one equation 1. Why not? Okay. The coefficient of restitution is going to be about the S. I guess that's the sphere, and point B, right? That's really where the bouncy takes place. So that's where we have to take the coefficient of restitution. And we see that we start out with 12, and we end up with and at 12 on the sphere and 0 at point B, right here on the left-hand side. And then on the right over here, this VB prime and the VS prime, that's going to be what we're looking for to put it back into this. So that right there is going to be the second equation. And between those two, we have two equations and two unknowns. And we're able to find what the VS, the sphere. And it turns out it keeps on going. Right? We'd be tempted to think that it would bounce off, but it really depends on the relative magnitudes right here of, first off, how fast and how heavy that sphere is, and then how light this moment of inertia is going to be. So that's an interesting outcome, and got to be wary of that. Now, I did not solve for what omega would be as part of this problem. But we could definitely do that. And if we did the omega, like all we would really need to do is solve for VB right here. Okay, so we do know that VB prime is going to be the 3.36 plus 9.6. That's pretty amazing right there. So it's going to be 12.96. That doesn't seem right to me somehow. Yeah, these kinds of things, it doesn't seem like that would make sense, but I guess so. It's kind of interesting that this rod's actually going to be moving faster than the ball originally was. That doesn't really pass the sniff test for me. But let me test that out right there. When I say, what's 12 times 0.8? Yeah, okay. It's going to be the difference between them. So, sure, I guess it must be, right? Yeah, okay. Well, it's kind of an interesting outcome. Not something that you would necessarily trust. I kind of almost want to test this out. So let me pause this show, and I'll discard all this, and we'll see what happens with a model. Okay, well, I built the model over in SolidWorks. SolidWorks Motion here. I gave these things the mass properties and sort of a basic dimensions. And I also put the coefficient of restitution is in the solid body contact right here. You can see that it's 0.8 right there. And I ran the thing. I had to mess with it a couple times, and here's a plot of the blue line is the velocity of the ball. By the way, this has to be in inches per second because they don't do the feet in SolidWorks. There's not an option that they have. Not at least, I don't know. Maybe I could dig a little deeper. But anyway, this is in inches per second. So it's 100. Starts off at 144 inches per second, and then I also plotted the x direction of vertices right there. It's not exact. There's going to be some differences because I decided to move the ball up just a little bit so it wouldn't hit right here. It would hit just a little bit higher. So there's going to be some difference based on that. But we could run the simulation here, and we could see, boom, yes, that it does go. The piece does go where we expect it to. Let me move this back over to the left because. Let's see, so I'll go over here a little bit. Okay, and hit play again. All right, so it's because the frames are skipping because I have this graph up here. Anyway, what I can do is I can right-click onto this graph and export to Excel, and I have over here, right? And I changed this was what came out of the thing. And then I just divided this column by 12 and this column by 12. And you can see it goes 12, 12, 12. And then at the moment of impact afterwards, this is going 3.15 compared to the 3.36 that we got from our calculations. And then before I turned this thing off and made the model, I got an interesting result where I'm predicting that that point, which we called B, was going to be moving more than 12 feet per second. And sure enough, and I calculated like 12.96, and look, we got 12.9. Of course, it starts to get smaller just because it's actually moving in an arc. Right, it's moving in across this arc. Let me shut off this graph here, and maybe that'll make the plot of this look a little bit better. Yeah, you're just not seeing all the frames that are taking place. There you go. You could actually see the impact there, and check it out in terms of like how the ball slows down. Right, and once again, I didn't put gravity into this piece. But you could see how that ball acts to get that thing going right from the beginning, huh? And, if I wanted to be a sort of interesting thing, like let's say that I wanted to mess around with this, I'm not sure this will work, but let me try it anyway. What would happen? Oh, I'm going to have an issue with I was going to make the coefficient of restitution be 0, but there'll be a little bit of a problem with that in terms of it sticking in to the thing, because I've set this ball. Its plane is 100% in contact with. I set the mate. Let me see. So I have to fix this up. Well, one of the problems with SolidWorks motion things. It's very sensitive to it adds these little key things. I forget what these things are called right here. What they could say, view keys or create key location. And so I think I have to. Yeah, I disabled them. Okay, it makes little events if you make a change and it isn't like in the starting position. But let's see this. Coincident right here. I'm going to turn this one off, right? So I made that one, actually, I made that a distance so I could make control with those distances. So I'm going to suppress it. And I think the only thing now, it's going to stay that initial position right here. And here, I'll calculate the thing out again. Hit that calculate button, boom. It's got no problem there. Nothing changes. And I think I have it set there. Okay, so if I was to take a look at that plot again, there's no change right there. But let me try, I can mess around with this a little bit. I can go try this out and change the coefficient of restitution. Let's make it 0. Let's make, let's see if it'll let me do that. Ah, there you go. Okay, so it didn't stick to it, but it did keep on going. So we can see what the values are going to be right here. Oh no, I want to show. I didn't want to replot, so I want to show plot. Interesting. They ended up with they share the relative velocity becomes the same right here. That's interesting. Okay, what would happen now if we make it perfectly elastic? Let's see if we have what is our effect going to be? Oh, we have to start from the beginning too. By the way, I think even though I said to turn the key thing off, I think it's going to mess it up. So I'm going to start from the beginning so it doesn't like change the properties from wherever the key happens to be. So let's make this into 1 and run it again. Oh, wow, now it really slowed down. It really slowed the ball down. And you can see a big jump right there, right? So would it even tell me what the value is right here? It says 171 inches per second. And we can divide 171 by 12 and get this. It's going to be like 14.25 feet per second. That's sort of an impressive thing. Now we could mess around with a bunch of other stuff. All right, so we have that option where I went and gave the properties of this. We went into evaluate, and I went into mass properties. I'll rebuild it. Sure, I think it's gonna be fine. I decided, let's see, I get rid of this, and I only have that part in here. And I went override mass properties. That's where I made it 4 pounds. Let's make it 10 pounds, right? So this thing, now the rod got pretty heavy. And you can see right down in here that it's 10 pounds, right? So the mass moment of inertia is also increased, but it's got the stupid units in there. So let's see now what happens when we run it again. And it has, look, the ball bounces off. That's so it's because this thing is so heavy that that it's doing that. And by the way, I constrained this these guys right here so that like it would be the axis. So I could go like maybe negative 50. I'll go negative 50. Let's see. It should. I don't know if that's going to be enough, but we go here. I'll do this one too. Make him negative 50. Negative 50. Right. And sure enough, see the ball is going in the opposite direction now. And we can play around with this. We can try to see what happens. It's kind of an interesting type of thing. I should be doing more of this. It's a pretty interesting. Like what would happen if you go 0.5? Let's try 0.5. And oh, by the way, I noticed. Do I have friction on there? That's interesting. I think I might have forgotten to take friction off. Yeah. I don't know how close we would have gotten over there with if I had left friction off. Okay. Hopefully I didn't. I forgot to start this whole thing back up. So let's see. Let me check this and see. Did it do that keystroke thing? No, it didn't. Okay. A view key thing. So we hit calculate again. Wow, that thing really slowed down right there. Boom. But it didn't reverse. Right? Yeah. That's pretty cool. Pretty interesting. Makes it a lot more obviously it's not realistic, but it should make it more realistic because it's just a thing, right? It doesn't know what is real and what isn't real. It's just math. Anyway, thanks a lot. Let's do another one.